Hello and welcome to follow my videos. My name is Matti Ylitalo and today our focus is on condensing. Just a second, I'll put the presentation mode on. In this video we will focus on condensing on a cold surface. The typical situation is something like this. We have a cold wall and here we have, for example, airflow in which we have some moisture. And if this temperature of this plate is low enough, we will have some condensing on that surface. Let's have a closer look how we can analyze this kind of situation when we have moisture in the air, we have cold surface and some moisture is condensing on that surface. We need some basic terms, and if we start from this humidity, it is a measure of how much we have moisture in the air. We are using two different kinds of humidity terms, and if we start from this absolute humidity, it is a measure how much we have water vapor in a specific volume of air. So it is grams of water vapor per cubic meter of air. Then we have this relative humidity. It is a measure how close the air is to being fully saturated with water vapor at its current temperature. For example, if we have a 50% relative humidity, it means that the air is holding half of the maximum amount of water vapor which it can hold in that temperature. Warmer air can hold more water vapor than cold air. Then we have this dew point. Dew point is the temperature at which the air becomes completely saturated and the water vapor begins to condense into the liquid water droplets. In this picture we have water boiling curve. We have temperature on x-axis and we have pressure on y-axis, here in kilopascals and here in bars. And if we take an example, so we have a temperature 100 degrees C and we are operating in normal pressure 1 bar. So we are here on this boiling curve. If the temperature is lower, our water is liquid, but if the temperature is higher, then we have steam. If we are operating at higher pressure, then this boiling point is increasing. At 2 bars, the boiling point of water is around 120 degrees C, and if we are operating at very high pressure, then this boiling point can be over 300 degrees C. These are typical values for power stations. Here we see steps which we need to calculate the amount of condensing water. The air, which is having some moisture, is coming from here, and we have cold surface here, and some moisture is condensing on the surface. So the step 1 is that we need this air temperature and relative humidity, and then we can calculate this vapor pressure at this temperature. And this actual vapor pressure is this relative humidity times this vapor pressure, and the humidity ratio can be calculated from this function, and That was the mass of water vapor divided by mass of dry air. And here is this constant, and it's explained here from which it is coming. It is the molar mass of water divided by molar mass of dry air. The next step is that we need to calculate this humidity value at surface temperature. We use saturation vapor pressure at surface temperature, and when we have the calculated humidity values, we can calculate the amount of condensed water. The most important key factor affecting on condensation is the surface temperature. The surface temperature must be below this dew point before condensation can happen. As a rule of thumb, we can say that the lower the surface temperature is, the faster the air is cooling nearby the surface, the more water is reaching this saturation point. And air humidity affects so that if the relative humidity is high, the condensation is much more likely. Air velocity affects so that if the velocity is high, it's bringing more moist air near the surface and increasing the condensation. And the higher the surface area is, the more we have a contact area, and it's increasing condensation. And if we have forced convection, it means more condensation. And if we have natural convection, then this condensation is typically very small. We can use also mass transfer rate to calculate the amount of condensing water. Here we have mass transfer correlations for laminar flow and this one for turbulent flow. Here this SH is so-called Sherwood number, and the mass transfer coefficient can be calculated as a function of this Sherwood number and so-called vapor air diffusivity. And the mass transfer rate is this mass transfer coefficient times this concentration difference between surface and bulk gas. There is one thing which I want to point out, it's this velocity. In this kind of cases, the velocity always means the velocity parallel to plate. And that's because in this kind of cases, the boundary layer correlations assume flow along the surface. And these boundary layer correlations take into account the hydrodynamic boundary layer, concentration boundary layer, and thermal boundary layer. If you have a case in which your velocity is towards the plate, then you need to move to so-called impinging jet mass transfer correlation. When we were talking about mass transfer coefficient, there was this diffusivity. Diffusivity, which is also called mass diffusivity or binary diffusion coefficient. It describes how fast molecules of one species spread out into another gas. For example, water vapor or ammonia into air. The physical meaning of this diffusivity is that if diffusivity is high, vapor molecules move quickly through the air and moisture reaches the cold surface faster and condensation increases. Here are typical values for water vapor in air, ammonia vapor in air, CO2 in air, methane in air, and we see that this water vapor in air has the highest diffusivity value. And here is described what is the difference between ammonia and water vapor. Ammonia is a little bit heavy, but the bigger reason is that ammonia has strong polarity and hydrogen bonding. It interacts more strongly with the air molecules. And then there is also this molecular collision properties which differ between ammonia and water vapor. The net effect is that ammonia vapor reaches the surface more slowly than water vapor under the same flow conditions. Let's take an example. This is a condensation from air on a cold surface. And I asked a Python code from ChatGPT, and using that code I calculated a case in which I had air temperature 25 degrees C, 75% relative humidity, and the velocity of air was 1 meter per second. And here we see the condensation rate in grams per square meter in hour. And on x-axis we have surface temperature. And we see that when the surface temperature is minus 10 degrees C, then this condensation rate is over 400 grams per square meter in hour. And when the temperature is around 20 degrees C, which is the dew point of our case, then this condensation rate is of course 0. Here we have another example. This is a flue gas condensing in a stack, and also in this case I asked the Python code from ChatGPT, and I calculated a case in which flue gas mass flow was 120 kilograms per second. Flue gas inlet temperature was 68 degrees C, and from this picture we see the amount of condensing water. It's in kilograms per hour, and on x-axis we have outlet temperature. The code is calculating also the recovered heat. It's based on this latent heat. Here we have an example in which we have condensation from gas mixture. So far we have been modeling cases in which we have only water vapor in air. Now I added also ammonia and CO2. Let's have a look how we calculate that kind of cases. I calculated this case in ChatGPT, and I assumed that the temperature of the incoming gas mixture is 25 degrees C and its water vapor mass fraction is 25%. Here we see how this calculation goes. We need to move from mass fraction to mole fractions, and from these mole fractions we get this partial pressure for water vapor. We need water vapor partial pressure also at surface conditions. Then we need to calculate the water vapor concentration in kilograms per cubic meter, both for bulk conditions and for surface conditions. And the so-called driving concentration is the difference between these two values. We need also calculate the mass transfer coefficient, and that was a function of a Sherwood number and this diffusivity. And when we have these values available, we can calculate this condensation flux for water vapor. Now when we have some ammonia in our gas mixture, we can ask how much ammonia is condensing. The answer is very simple, not at all. And the reason is that ammonia's normal boiling point is minus 33 degrees C. So in this case ammonia will remain in vapor phase. Here we see the ammonia vapor pressure curve. If you want to remove also ammonia from gas phase, you should consider absorption into liquid film or semi-sorption, not this condensation. I asked ChatGPT to give examples of gases which will condense if our incoming gas temperature is 130 degrees C and our surface temperature is 0. And it was explaining that those gases which have boiling points above 0 will condense. And here are examples. For example, water vapor, and acetic acid vapor, methanol vapor, ethanol vapor, most heavy organic vapors, hydrocarbon vapors, and which will not condensate. Here we have examples of those gases. For example, nitrogen, oxygen, carbon monoxide, methane, hydrogen, helium. Here we have an example in which we are modeling condensation in a vertical duct. The gas is coming from here, and in this gas mixture we have water vapor and some non-condensable gases. And the cross section of the duct was 0.1 meter times 0.1 meter, and the length of the duct was 20 meters. The input gas temperature was 70 degrees C and relative humidity was 25%, and the velocity upwards was 5 meters per second. In this picture we see how the water vapor concentration is changing. On x-axis we have the duct length, and on y-axis we have water vapor mole fraction. And it's coming down from around 8% down to around 1%. And here we have the cumulative condensed water amount. And in this picture we see how the gas temperature is coming down and how this vault temperature is changing in this case. I asked a summary of what we have now in that model, and the main limitation is now that this is one-dimensional axial plug flow model, and it's having mass transfer limited condensation process. The film hydrodynamics is very simple in this model. Then I asked also proposals for development, and seems that the highest priority is here. We should develop this energy couple, but there are many other proposals also. Okay, that was all this time. Thank you for watching, and I hope that you got an idea how we can model this kind of cases. See you, bye bye.